Welcome back to Catalyst University. My name is Kevin Tokoff. Please make sure to like this video and subscribe to my channel for future videos and notifications. And a big thank you to my patrons on Patreon for your contributions to my channel. In this video, we're going to be discussing the mechanisms underlying the development of atherosclerosis. But before we get into all the atherosclerosis mechanisms, we need to understand the difference between laminar and turbulent flow. And of course, flow refers to the blood flowing throughout the vasculature, especially in the arteries, which is where atherosclerosis tends to occur. Okay, so over here on the left, we have a picture representing laminar flow. Notice that each piece of the fluid, as it's flowing parallel to the vessel walls, it's a very smooth, parallel flow, and it tends to produce shear stress against the walls of the vasculature. And even though it has the term shear stress, this actually turns out to be a good thing. Okay? Notice how smooth and streamlined this flow of fluid is relative to the vessel wall next to it. Now compare that to turbulent flow, where if we look at the regions of the fluid that are traversing next to the vessel wall, it's not smooth, it's not streamlined, it's turbulent. And it's not able to produce this kind of shear stress against the vessel walls. Now, laminar shear stress. Okay. Despite the fact that this has stress in the name, it's not actually a bad thing. So laminar shear stress, areas where we have that, have to have laminar flow, and that shear stress that's produced is associated with these three things right here. One is nitric oxide production. So in the endothelial cells, there's an enzyme called endothelial nitric oxide synthase. And so when there's shear stress on the walls of the vessels, meaning those cells, it tends to increase the activity of that endothelial nitric oxide synthase, and the cells secrete nitric oxide. And this allows vasodilation, and it allows the vessel to not become constricted and basically remain open so that you get as much flow of blood through that vasculature as possible. So nitric oxide is good. We also get the production of something called Kruppel-like factor, or KLF2. This is a mediator of the immune response. And basically what it does is it prevents certain aspects of the immune system from occurring, basically minimizing unnecessary inflammation. Generally speaking, if we have unnecessary inflammation, that is a bad thing. So Kruppel-like factor keeps that in check. And then we also have the production of this enzyme, superoxide dismutase. This is an enzyme whose reaction is to take the molecule superoxide and convert it into hydrogen peroxide, which will eventually be degraded. And so in this way, superoxide dismutase protects us against reactive oxidative species, one of which is superoxide. And just understand there's another enzyme to deal with hydrogen peroxide. And superoxide dismutase is also anti-inflammatory by virtue that it helps get rid of reactive oxidative species. And again, we're going to get the production of these three things in areas where we have laminar shear stress. Now, areas where we have turbulent flow do not have laminar shear stress, and so these three things are going to be diminished. And that's going to come to play in a few minutes. But the other thing I also want to mention is that places where we tend to have turbulent flow are where the vessel radius is larger. So medium and large vessels tend to have more turbulent flow. So smaller vessels are going to have more laminar flow. And the way we determine if there's turbulent flow is by calculating what we call the Reynolds number, or RE. And so the formula for Reynolds number is you take the density of the fluid times the velocity of the fluid times the diameter of the pipe. In this case, the pipe would be the blood vessel, lumen, and then in the denominator here's the viscosity of that fluid, and of course the fluid is blood. And so you throw a bunch of numbers in here and you get a Reynolds number. And in general, if Reynolds number is less than 2100, you have laminar flow. If it's between 2100 and 4000, then it's somewhere between laminar flow and turbulent flow, so it's in transition. And then if Reynolds number is greater than 4000, it's turbulent flow. And what I want you to notice here is in the numerator here, the diameter. Okay? If the diameter of a vessel's larger, it's a larger vessel, right? And so if you increase the diameter, you increase Reynolds number. And increasing Reynolds number tends to mean more turbulent flow. So the larger a vessel radius is, or its diameter, we could say, the more likely it is to have turbulent flow. And so that's an important factor. Larger vessels are going to have more turbulent flow. In addition, Places where we have bifurcations in the vasculature are also going to be subject to turbulent flow. So look here at the aortic arch. We know that we have three vessels that are coming off of this. We have the innominate artery or brachiocephalic artery, and then we have this would be the left common carotid artery and the left subclavian. And of course, you can see bifurcations right here where it divides into two. Here's another bifurcation over here of the left subclavian artery. One's going up to the neck and the other is going into the axillary artery. Okay? So these areas where we have bifurcations are also subject to turbulent flow. Now, why is this important? Because areas where we have turbulent flow are more susceptible to atherosclerosis. Now, does that mean that turbulent flow is the cause of atherosclerosis? No, but it just means that areas where we have these bifurcations or larger vessels, those tend to be the sites of atherosclerosis most of the time. Now let's talk about the endothelial cells. These are the cells that line the lumen of the vasculature, of the blood vessels. So the blood is in direct contact with these cells. And when they're healthy and functioning normally and you don't have any vessel injury, they normally produce molecules which are antithrombotic. That means that they prevent unnecessary blood clots. If you don't have any tissue injury, it doesn't make sense to produce a blood clot, right? There's nothing needing to clot. Okay, so they should prevent that process from happening according to their baseline function. But whenever those cells are subjected to physical and metabolic stressors, and we'll talk about a few of those in a minute, they can start producing prothrombotic and pro-inflammatory molecules. Because in theory, if there actually is vessel injury, you need to repair that injury and potentially destroy any foreign invaders like bacteria. So it would make sense to have pro-inflammatory molecules to help fight an infection, bacteria, virus, whatever it happens to be that's invading. And also if there's an injury, prothrombotic, you're going to need to cause a clot to occur to prevent blood from escaping, right? So some of the stressors are listed over here, and the first one is turbulent flow. Now I mentioned we can't really do much about that, okay? So larger vessels and areas of bifurcation have more turbulent flow, but that's just to say that those sites are going to be more susceptible to atherosclerosis. But look over here, hypertension, high blood pressure. Okay? Higher blood pressure means more force against the cells of the vessel wall. That's a stressor. Bacterial products, lipid products, advanced glycation end products. Advanced glycation end products are a big problem for individuals who chronically consume a lot of sugar. It causes the blood to have a higher sugar concentration, and sugar covalently attaches to proteins and to other things, and it causes them to become inflammatory and induce an inflammatory response. Hypoxia, so low oxygen concentration, excess acid, viruses, and cigarette smoke. A lot of the things in that, like benzopyrene, are known to damage endothelial cells. And so when they become damaged, or there's metabolic or physical stressors, they start changing their metabolism from antithrombotic molecules to prothrombotic and pro-inflammatory molecules. And that state is considered their activated state. We only want those cells to become activated if there's an actual threat. An actual threat being something like an invading bacteria or something like that. A lot of these things over here have to do with lifestyle choices. No one's forcing you to smoke a cigarette, okay? No one's forcing you to eat a lot of sugar. Now, if we're making poor lifestyle choices and we're getting these endothelial cells to switch into an activated inflammatory state, we're going to see some changes. Okay? The spaces between those endothelial cells are going to increase in size, meaning you have increased permeability. Things can slip through between the cells that we don't usually want to, like LDL cholesterol. Number two, we get increased inflammatory cytokine production, so furthering that inflammation. We get increased leukocyte adhesion molecules on cell surfaces. So I mentioned this increased permeability. Well, one of the things that can also slip through the cracks, so to speak, between those endothelial cells are white blood cells, so leukocytes. And they don't just slip through, though. They actually have to adhere to the cell surface of the endothelial cells before they can slip in. Okay, so it's kind of like you have to knock on the door before someone lets you into their house, right? So just like that, the leukocytes have to attach to the cell surface via cell surface receptors called adhesion molecules, and then they can slip through the cracks. once you have that increased permeability. But when we have these pro-inflammatory changes to the endothelial cells, they start expressing more adhesion molecules because they think there's a problem. They think they need to have inflammation, and so they're going to get more leukocytes to the area. And also, there's a decrease in vasodilatory molecules like nitric oxide. Less nitric oxide means less vasodilation and overall more constriction by default. Now, here's where we're going to start seeing how some of those changes can lead to the development of atherosclerosis. So those chronic stressors that we just talked about, okay, they're going to cause the endothelium to no longer serve as an effective barrier to circulating lipoproteins. Remember, we have lipoproteins in the blood that transport lipids like cholesterol. LDL is a great example of that transports cholesterol to peripheral tissues. Okay. Remember, we have that increased permeability, so increased space between the endothelial cells. Not really shown well in this picture here, but there is increased space there, and it can allow LDL to enter into the intima. Basically, what we mean by this is just the space deep to those endothelial cells. Okay. Now, it is true that LDL will be able to enter this area right here in white, the intima, when you have increased permeability. However, what we also know is that for people that have chronically elevated insulin levels, so hyperinsulinemia, which is caused by high sugar diets, so excess sugar in the diet, it actually causes alterations in LDL size and shape. So if you consume a lot of sugar chronically, what will happen is your LDLs will actually decrease in size. The liver is pumping these things out, and they actually are a different shape than what they would normally be in a healthy individual. And so if the LDLs are smaller, it makes it easier for them to fit through the spaces between the endothelial cells. And actually, you can actually have LDLs get into the intima even without this increase in permeability. However, they tend to occur together. And I have a separate video where we talk about the effects of high sugar diets and hyperinsulinemia on LDL size and shape. So go check that out. It'll be in the description of this video. But again, that increase in permeability allows LDL to go from the vessel lumen, so in the blood, into the intima. And you can actually see some of those LDLs coming in right here. Now, those LDLs that you can see coming in here into the intima, they just go by passive diffusion because they're moving between the spaces between the endothelial cells. They accumulate in that subendothelial space by binding to components of the extracellular matrix, and they basically become trapped. And in the intima, the LDL tends to undergo chemical modifications. So in these individuals who have these chronic changes to the vasculature, they're going to have higher levels of reactive oxidative species than a healthy individual. Okay, so those reactive oxidative species, free radicals in other words, are going to chemically modify the LDL. Okay, it doesn't require an enzyme, it just happens because they're present, right? And so that's going to cause oxidation. Also, like we said up here, you would tend to have these changes also if you have elevated sugar in the diet, refined sugar. And so that sugar is going to glycate the LDL, and that's going to also chemically modify it. These modified LDLs, which are sometimes called LDL ox because they're oxidized LDL, they accumulate here in the intima, and they trigger macrophages, which are immune cells, to uptake them. The macrophages are like Pac-Man, and they basically, as you can see right here, they eat the LDLs. Okay? When macrophages eat the LDLs, the macrophages will differentiate into a new type of cell called a foam cell. Foam cells are not intrinsically bad, it's just that in these individuals who are on the road to atherosclerosis, they tend to make a lot more foam cells because there's a lot of oxidized LDL in the intima. And so when these foam cells form, along with the macrophages, they will secrete pro-inflammatory cytokines, which basically trigger more inflammation and recruitment of more immune cells. Okay? And what you see over here is eventually the foam cells can actually undergo apoptosis, or worse, necrosis. So apoptosis is controlled cell death. Necrosis is basically just the cell bursts, and it's not pretty. Okay? And when the cell undergoes necrosis, everything inside of it spills out. Okay? And since the macrophage basically initially consumed LDL, which contains a ton of lipids, when this foam cell explodes and undergoes necrosis, all the contents, which are lipids, spill out and they aggregate. Okay? Lipids don't like water. If you do this experiment where you put oil and water together, what happens? The oil, which is a lipid, all sticks together on the top of the water. Okay? Lipids stick together. And so what you'll have is the formation of a lipid-rich necrotic core, which you see right here. Now initially it won't be this big, it'll just be a little bit. But lipids aggregate, they like to stick together. And as it gets bigger and bigger, it's going to tend to trap more macrophages and foam cells. They kind of just get stuck within it, and then they die. And so it's basically just a lovely place of death. When we get this lipid-rich necrotic core initially forming, it's called a fatty streak. Okay? The fatty streak is basically the lipid aggregate, or the lipid-rich necrotic core, that's not yet surrounded by vascular smooth muscle cells and collagen. In this picture down here, it's already surrounded by these smooth muscle cells in pink. Okay? But initially it won't be. And while it's not surrounded by collagen and smooth muscle cells, it's just a fatty streak. And when you have the fatty streak, it actually does not protrude that much into the vessel lumen. It doesn't restrict blood flow as much as you would think. And it's also reversible. Okay, so the fatty streak can be reversed with diet and exercise, and it doesn't necessarily occlude blood flow. But what happens now is something that will lead to that, the formation of the fibrous plaque. So some of the cytokines that are released can cause smooth muscle cells, or vascular smooth muscle cells, to proliferate and differentiate. And these vascular smooth muscle cells will migrate into the area of the lipid aggregate right here. And you can see they're kind of on the other side here and kind of bounding it next to the endothelial cells. So these are vascular smooth muscle cells. And in the same way that a fibroblast would, these cells are going to secrete a collagen. And the collagen we normally think of as almost like scar tissue. Okay, so they're depositing collagen here. When both of these things occur, you now have a fibrous plaque. Okay, so if this collagen and these smooth muscle cells weren't here, it'd just be a fatty streak. But once you have the production of the collagen, it's kind of just making some scar tissue here, more or less. Now it's called a fibrous plaque. Okay, and this is going to be much larger than the fatty streak. It is going to protrude into the vessel lumen, and it's going to start to obstruct blood flow through the vessel. And many times it will also start to be covered by calcium deposits. Eventually, this fibrous plaque can become worse and worse and worse, and you can get continued inflammation that can result in plaque instability, ulceration, or rupture. Notice right here in this picture, you can actually see that it's ruptured a little bit. Okay? When this ruptures, the lipid-rich necrotic core is exposed to the blood vessel lumen. So out here is the blood. This is where we have platelets and so on and so forth. Well, once you get this rupture right here, now the lipid core is exposed to the blood and platelets. And you get platelet adhesion, and then platelet aggregation, and then thrombosis, the formation of a blood clot, which you kind of see right here in the picture. And eventually, that can further narrow the vessel lumen and also lead to a thromboembolic event, because if this blood clot breaks loose, it's now embolized and is mobile, and it's an embolus, and it can go to the heart, and it will potentially occlude a coronary artery, and you can have a heart attack. Okay? Or it could potentially go to the brain and cause a stroke. And you can also have vulnerable plaques and stable plaques. And that really has to do with the amount of the collagen that's been deposited that separates the lipid core from the lumen of the blood vessel. So in this vulnerable plaque right here, it's vulnerable because there's only a very thin layer called a fibrous cap here, which has a lot of collagen that's separating the lipid core from the lumen. If you have that continued inflammation that destabilizes the plaque, it makes it more likely to ulcerate or to rupture, which again would expose that lipid core to the blood, and then you'd have the platelet events. Over here you have a more stable plaque, and it's more stable because this fibrous cap, which of course contains the collagen, is much thicker. And so even with inflammation that continues, it's going to be less likely to rupture and expose that lipid core to the blood where the platelets are. Okay? Now again, in neither of these cases is it good. Okay, I mean, I guess you could argue that a stable plaque is better because it makes it less likely to have a thromboembolic event from this, because there's less likelihood of rupture. However, in both cases, notice there's obstruction of the lumen and a decreased volume of blood that can go through that area at any time. Okay, normally this lipid core wouldn't be here, and you'd have a much larger vessel lumen. So in both cases, they do occlude blood flow to some extent. This picture over here is showing some of the same stuff we just talked about. But over here, what I want you to notice is there was a rupture of that fibrous cap. Now you have over here the lipid core exposed to the blood, and a blood clot has formed right here. Now that blood clot may initially just stay right there. Okay? It's still occluding blood flow through this vessel, but it's less dangerous when it's stable and stuck right there. But if it were to break loose, it would start flowing through the blood. And it would keep flowing until it gets to a vessel that's small enough where it gets stuck. And an example of that would be in the coronary arteries. And so when that embolus basically gets to the left ventricle, it's going to be pumped out to the aorta, and right here it would go through the left coronary artery, and those vessels tend to be small enough where eventually this embolus will get stuck and occlude blood flow, and now this area of the heart no longer is getting adequate blood supply, and there is your myocardial infarction or heart attack. So hopefully this video gave you a decent understanding of how we develop atherosclerosis and what factors are involved and how it can potentially lead to an acute myocardial infarction. Thanks for tuning in. Please like, subscribe, and check out my Instagram for cool science and not science stuff.